Now we can go. Okay. Are there any questions? I think, okay, some people in the audience and they already asked me. I suppose to ask at the beginning, do we need, I don't know, to somehow push deadline to concern the problem for the first lecture? But I mean, probably all people from Russia now who plan to pass this course in the audience, and they already told me. Today I'm going to finish my second lecture, which I stopped somehow in the middle of my plan, and so it will be lecture 2 and lecture 3, both will be about the same subject, affine algebras. And let me first briefly recall where are we, what is our place. So we defined affine Lie algebras. Today there are no quantum groups as a loop algebras. We defined its Cartan, its weight decomposition. Then we stated this affine Kac-Moody Lie algebra, and I decided to put this even as a problem to show that the generators which we defined in the lecture satisfy relations of Kac-Moody Lie algebra, namely quadratic and sphere relations. Of course, this is just a statement about E0 and F0, and more or less this is transparent, but maybe it's good to follow the notations and prove it. It is sufficient to restrict to the simply laced case, because I mean, if we have, for simplicity, we do this. So this is another presentation of the affine Lie algebra in terms of the Chevalier generators. Here are our two examples. This is my slides from the last time, but somehow improved. I mean, I want them to look better. And here's a Borel I draw Borel subalgebra for the affine SL2, and Borel subalgebra for affine SL3 is something like this. Maybe I can also draw it even now in principle. Why not? No, not good. Once again. Okay. More or less like this. And in general, the algebra, as any Kac-Moody algebra, has triangular decomposition. N minus part, Cartan part, and N plus part. N plus is subalgebra generated by E0.ER, and minus is subalgebra generated by F0.FR. And next subject is affine Weyl group, and this is where we stopped actually last time. Affine Weyl group first defined as usual the group generated by reflections corresponding to simple roots. Now we have additional affine simple root as 0. So it will be group generated, not affine, ordinary Weyl group generated by S1, so on SR, and also we have one more generated as 0 with a similar form of the braid relations. And this group can have natural representation. So by definition, it acts on the Cartan, or here I speak about dual space to the Cartan. And this space is R plus 2 dimensional. R is the rank of the original algebra G, and it has two additional elements on the basis: imaginary root delta and a fundamental root corresponding to the zero's fundamental weight is omega 0. Here here I draw the for completeness the scalar product of them. So I assume that everything is semi-simple, then simply laced. Then here we have just done that scalar product between alphas, and delta and omega 0 are dual. It is not necessary to have simply laced, but just this is not necessary for this formula. It doesn't matter. We have formula for the and the affine group acts here generated by reflections. So we have reflection with respect to this R roots and also with respect to alpha 0. Alpha 0 is delta minus theta, and delta is the imaginary root, and theta is the highest weight of the joint representation. For the SL R+1 case, theta is the sum of all alphas. Okay. So it is transparent to calculate scalar product of alpha 0 with any of this, and so we define the actions. This definition, now a few remarks I know. First of all, I defined the group by reflection with respect to simple roots. Actually, reflection with respect to any root belongs to this group. This is as in a fine dimensional case. One can show that this group, using this simple generator, we can move any root to any other root. So, and so hence, any reflections conjugate to one of the reflections with respect to simple roots. Hence, any reflection belongs to this group. The second remark that delta is orthogonal to all simple roots. This is by definition, because here we have zeros, and alpha 0 is again delta minus theta. Delta is orthogonal to itself and orthogonal to theta. Hence, delta is invariant under any reflection. Here we have 0 in the numerator. So this R plus 2 dimensional representation is not reducible. It has one dimensional submodel. So it is natural to ask for smaller representation, because R plus 2 is not, even for SL2, it will be three-dimensional representation, so it will be difficult to draw pictures. But we like to draw pictures, so we ask for smaller representations. And one way is to take just a subspace generated by all alphas, and this subspace is invariant, because you see everywhere when we take reflection, we shift our vector by sum of alphas. So this subspace is invariant. We can take either alpha 0 or delta, and this are just one dimensional of the representation. The disadvantage of this space is that our form is degenerate here. So our form is given by this submatrix, and you see delta is 0. Delta belongs to the kernel of this form. So this is a standard definition of our representation, but with but form is degenerate. There is another way, which denoted by B, which leads to affine representation. And by word affine, I mean this is, in this case, the group will be represented not by linear operator, but by affine operators. And the formula is here. We take affine hyperplane, so it is a omega 0 plus any linear combination of roots alpha i's. It takes the quotient by the subspace generated by delta. So what in order to check that this definition is correct, what should we do? We should say that numerator in this quotient is invariant on the action of the while group. Why? Because any reflection adds some alphas. So we change this coefficient by the coefficient with respect 1 in the near the omega 0, pi 0 will be constant. Second, we should say something about this delta, and as I said, the delta is invariant. So we can take the quotient and we have action of the affine while group on this quotient. Here is the picture. So a bit symbolical, but I don't know. If you have any idea how to improve it, then say it. So this is 0. This is the space from the representation case A. This is a linear combination of all roots. In this space, we have one-dimensional subspace generated by delta, which is also invariant. Now, with this, we move this hyperplane up, adding this omega, this pi 0. So we get a affine hyperplane, which is not going through 0, but still it is invariant. So this hyperplane is invariant, and this hyperplane is parallel to it, it is also invariant. And then we take the quotient of this hyperplane by delta and get somehow a affine hyperplane dimension 1 less. So this has dimension r plus 1, and after the quotient we have r dimensional affine representation of the affine value. We have example of SL2 case A. Maybe will not recall, we had it last time, but case B, let me say it once again. So in the numerator, we have this affine hyperplane. So we have pi 0 plus alpha with any coefficient plus delta with any coefficient. So linear combination of such this space which consists of such vectors. And on the denominator, we have we take the quotient of a subspace generated by delta. So any representative of this quotient is pi 0 plus x alpha plus this linear space generated by delta. So the quotient is something y-dimensional with coordinate x. And now we have to compute how to our reflection x on this space. And as a result of computation, we see that in terms of coordinate x, one reflection x by x to minus x, and another reflection x by x to 1 minus x. So these are two reflections, one with respect to this on the line, real line, I draw it. But one is the reflection with respect to 0, and another is the reflection with respect to 1 over 2. Okay. And my remark that we have also not simple reflection, but all reflection means that in the group we will have a reflection with respect to all other half integer points. This is clear. For example, we can have reflection with respect to this point as a composition, reflection with respect to this point, and again this point. This composition is reflection with respect to this point, and it is easy to see. Any such reflection belongs to this group, and also in this group we have translations. If we take composition as 0 in this one, it will be translation by 1. This translation is the element of the infinite order, and this is actually braid relations or some sort of absence of braid relation for the case of SL2. In case of SL2, this M, which we had in braid relation, is equal to infinity. Are there any questions about this example? Okay, if there are no questions, then let me move to the general statements. General statement is that this group, affine group, acts on the space generated by alpha 1, alpha r. This x is actually coordinates of the space and this actions generated by reflections with respect to affine hyperplanes. And the affine hyperplanes are given by the equations. The scalar product with v with alpha is equal to f. So these affine hyperplanes are labeled by the root and integer number. and maybe I should add this, that it is sufficient to consider roots to be positive and integer. Because if I take, alpha to minus alpha, it is the same to change n to minus. Of course, this is standard fact that that the reflection to positive and negative roots, they have the same orthogonal hyperplane, so it is sufficient to consider affine positive roots. And this is a affine positive root, but without imaginary ones. So maybe I should say that what is the mean of this 1/2? So it is in this picture, alpha is here, and scalar product of alpha with itself is equal to 2. So this is, in some sense, this is pi 0, and scalar product of pi 0 and alpha is equal to 1. So this is precisely this hyperplane. So this 1/2 comes from the fact that we use normalization, which scalar product of the simple root with itself is equal to 2. Another suggestive picture is the following. So we have our group is generated by reflections with respect to all lines parallel to this 3, and this 3 are, so we have these 3 lines which are orthogonal to the roots, which are, so this line is orthogonal to root alpha 2, this line is orthogonal to root alpha 0. Maybe I should draw that here is 0. And this line is orthogonal to root, which is alpha 1 plus alpha 2. And then we, in many ways, we move these lines by shifting them by integers. And some sort of kaleidoscope, if you want. And the final group is generated by reflection with respect to this line. This is the best way, I think, to visualize a affine value group. This is the smallest representation, r plus 2 dimensional. So for SL2, this is even too simple to draw just the line. I think it's convenient to recall. Okay, this is the point where we stopped last time, I think. Are there any questions? In which picture? In this picture, you see the ends of these roots do not belong to the lattice. Yes. Maybe this is wrong. Maybe this is wrong. Let me think for a moment. I think you're right. I think the ends of this line should belong to the lattice. So this is alpha 1, and this is alpha 2. Yes. So integer points here belong to the weight lattice, and these alphas they generate a sublattice which is root lattice. Maybe I draw the sublattice by bold. And so on. So this sublattice of index 3 should be for SL3. And if you want, okay, maybe other questions? Yes, so this sublet is vertex 3, so the quotient will be a group of order 3, so it will be C3. It's like a group of order 3, yes. Okay, so here I talked about all reflections. Now I come to now simple reflections. The Cauchy hyperplanes are determined by these formulas, and for all simple roots except affine simple root, the n is 0. So the hyperplanes is just a scalar product with v with alpha I is 0, and hyperplane which correspond to the affine root is given by this formula. So again, in this picture, so these are hyperplanes which correspond to the simple roots alpha 1 and alpha 2. And here is the theta, or better to say minor theta. So hyperplane correspond to this affine root is this one. This is now I come to the definition of the alcove. Alcoves are defined as a connected component in this space. In order to say about component, I need to consider everything over real. I'm a bit, maybe I'm not. So I wrote here word connect component. I don't want to, now I can write even where, so I can take some, say, weight lattice and multiply and take its real thing. So the connected components here, which in complement to H alpha n, and fundamental alcove is a component. Okay. Maybe it is not necessary to write because it is written here. So fundamental alcove is the alcove with a boundary given by this by hyperplanes which correspond to simple roots. For this case, it will be this segment. So alcoves are segments, and fundamental alcoves, it's just we pick one of the segments. Of course, it's not. It is just our choice which one to pick as the choice of simple roots. So we pick one. Now let me state theorem. Group WA acts on set of alcoves transitively and without kernel. Let free. So what I'm saying that each element is determined by the the group WA, which is generated by all these reflections, permute these alcoves. And if we know where the fundamental alcove goes, then we know the corresponding element. So there is a bijection between between alcoves and fundamental ones. This is stated in verse transitively and free. Okay, maybe I move picture up and say refer to it all the time. Here's after this geometric preparation, we can define the length function, the function of length function definition. I will say, put it in the following manner. The following three definitions are equivalent. A, length of element W is equal to K. W is SI1, SIK. It is shortest expression. It means so expression among which expressions? So we take, we consider ways to any element of the affine Weyl group is a product of simple reflections, and we take among this, we take the shortest one, and its length is the length of the element. So we define function L length from the WA to negative integer numbers. It will be 0 for identity element and positive for numbers. B. Let W of A is equal to A prime. Fundamental A, by A I here denote fundamental Markov. Then L of W is the minimal number of hyperplanes to cross from A to A prime. So if we, so this is our fundamental Markov. If we take any element which moves this Markov to say this one, then we take any path which goes from one. We consider all paths from this Markov to another one, and compute how many hyperplanes do they cross. And the minimal of these numbers is the length. For example, so length of the identity element is 0 because there's no hyperplanes to cross. If we take any simple reflection, then this A prime is neighbor Markov. So the length is equal to 1. If we take product of two simple reflections, then the corresponding I prime is a bit, the Markov a bit longer distance, and the length will be equal to 2, and so on. This is some sort of explanation. This is not completely obvious statement, but I just state. And the property C L of W is equal to number of roots of positive affine positive root such that W of beta is negative. Actually, all the for finite case we have the same statement. So equivalence A and C is the same as for finite for any Boxster story, and A and B is also the same. The only difference that instead of the Markovs we have Weyl chambers in finite dimensional case, and compute how we should look how when we cross the board the hyperplanes between when we go from one Weyl chamber to another. Okay, are there any questions? Everything is clear. The next topic about affine while group is its description in terms of the semi-direct product. It is better to see it on the again to look at this picture. So affine while group transitively freely acts on the set of alcohols. Now let us consider the origin. There is a subgroup in the affine while group which preserves the origin. This is a finite while group. So we have the finite while group. This is a group which preserves 0. I claim that any other element can be written as an element of the finite while group and translation. Indeed, any generator of a affine while group is a reflection with respect to some line which is parallel to the reflection which belongs to the W. So any element of the affine while group is some affine transformation, but the linear part of it belongs to the finite while group W. So any element is a composition of the element of the finite while group and the translation. And the claim is, okay, let me put it as a theorem, that affine while group is isomorphic to the semi-direct product of the finite while group and root lattice, where Q acts maybe I can erase everything here. By translations. T alpha applied to any vector x will be x plus alpha. I say this theorem is more or less clear. So I tried to explain that the affine while group is semi-direct product of the finite while group and translations. It remains to study which translation do we have in a affine while group. And by definition, any reflection shifts our x by some combination of the roots, some respect, and therefore the only thing which we can so therefore any translation shouldn't belong to root lattice. It remains to show that any translation with respect to root can be achieved, but this is clear because T alpha is composition of translation with respect to alpha 1 and alpha 0. If I take two parallel lines, then composition of the corresponding reflection will be translation with respect to alpha. So in this picture, it is quite seen. So I take composition of this to translation. So if I take some element and move it here and put here, so it will be translation with respect to the vector which is twice longer than the distance between these two lines. And this is precisely alpha 1. Okay, so this is theorem which is, I hope, clear. In some sense, you can compare this description. So we have two descriptions of finite while group. One of the as a semi-direct product of the finite while group plus some translation, something, and another is just as a standard while group for the Kac-Moody group. This is a group generated by reflection S0 and so on and so on. So this should be some probably similar to the two descriptions of the affine Lie algebra. One in terms of the Chevalier relations, another as a loop algebra. Okay. Let's look again on this picture. So I said that we have translation with respect to the roots. So to each triangle we can move this one. If we take such translation, we move it here. Okay, I will draw triangles in which we can come by some color. So we can come here. Using this translation, we can come here. Using this translation, we can come triangle which is not drawn, but clearly it is here. We have also this translation, so we can come here. What other things we can do? We can, using this translation, from here we can come here, yes? Probably also here. So why I draw all this? I want to stress that we don't have all that in principle there are more translations. In principle, one can imagine there is a translation which moves just this triangle to neighbor one, this one. This is just translation by this vector, or maybe opposite, this vector. This is the problem which we mentioned above. Actually, this lattice is larger than root lattice which we have already obtained. And it leads to the definition of the affine extended while group, which is no more Hochster group, which is not generated by reflections, but for which we have definition in terms of the sum indirect product immediately. So maybe not. Is sum indirect product of W and P. Recall that P is the weight lattice. And this actually is the largest group which we can imagine. There is any translation which preserves this set of hyperplanes should belong to the P. There is a notion of the length of this group. Let me say. This group have another description as the following. Okay, maybe I should write it as some sort of statement, not theory, maybe, but just position. So this group contains a affine group, and this is a extension by the finite group. And what is the meaning of this finite group omega? This is a group subgroup in affine extended while group, which preserves fundamental alcove. As I said, any element of the affine while group is uniquely determined by the alcove to which it moves the fundamental one. And this formula says that so in the extend group, we already have some transformation which preserve it. And we have some symmetric problem. It is true. Okay, let me state it as another proposition that omega is isomorphic to P quotient. So this is a corollary of these two formulas. maybe not this formula, and this formula. So affine extended is a omega times is a affine extended not extended times omega. On the other hand, the difference between affine and affine extended is the difference between P and Q. So this leads to this isomerism. Okay. Maybe any other questions or remarks? Geometrically, on this figure, what we add rotations with respect to the center of this triangle. We can rotate this group. In this case, is a cycle group for this tree. This is a group omega. In this case, we add additional reflection with respect to this even more, 1/4. This reflection preserves the set of the hyperplanes. This is the difference between affine and affine extended line. Affine while groups are, very interesting and I think important, and for many other topics, in spite of this one. But main reason why I talk so much about this, because we have action of the affine bright group on the affine quantum group by the Lüftig's formulas. So we have to say something about why affine bright group. Affine bright group is a very, of course, this is a relative of the affine wild group. So definition. Affine braid group. Okay, let me write it. Braid affine. This group is generated by. Okay, let me write it completely. We have generators now labeled from 0 to R. And we have the same relation as in affine, except we do not have, we no more have involution relations. Each ti squared is equal to 0. Now they are subject of yes. No. Q. There's a question about what we had here. Q is a root lattice, and P is a weight lattice. So the lattice you see here in this picture, we have roots, and they correspond to sublattice, which is somehow bolded one. And this is not whole lattice which we have in the intersection of the hyperplanes. So in this picture, P is all these points, and Q is bolded points. Yes, affine wild group is a WA, yes. We have this decomposition, and this explains. Any element of the affine wild group, it has some linear transformation plus translation, because it is a affine transformation. All linear transformation belongs to the finite wild group. And all translation which we can achieve by taking the composition of this reflection belongs to the root lattice. Let me say, give a bit even more simple example here. We take group generated by all such reflections. If we take composition of these two reflections, you get shift by 1. But this shift by 1 is a generator of the root lattice Q. You're asking about this translation. Yes? Yes, so this vector doesn't belong to Q. No, so this translation does not belong to the affine while group. It belongs only to affine extended while group. Yes. It is, so okay, let's discuss this example. So let's look at this translation. It moves this alcove to this one, alcove number 2. Yes, yes, exactly. So there is a transformation, which is composition of this reflection, which moves this alcove to, no, maybe wrong. We have to move this alcove to this one. So this such rotation, this alcove to alcove number 3, and then translation in this way. There's another transformation, which moves this alcove to this one. Okay, are there any other questions? Maybe not from the, it was a question from the people in the audience, but maybe somebody from Zoom wants to ask something. But of course, I encourage everybody to come and offline and ask questions offline. Okay, so the question was in the point where we define a affine braid group. So this is the group generated by T0 TR, subject of braid relations. Okay. Actually, this is last topic from the lecture 2, and so very soon we'll move to lecture 3. But I mean, very soon doesn't mean in a minute, but maybe in 10 minutes we'll finally start our lecture. There is a very interesting subgroup. So you see, and I'm making new problems. So I thought that something I will cover in lecture, but now not. So I move it to problems. But still, I want to cover at least something, and I want to define what is Y lambda. Before defining this, I have to. Okay, let me move it. All this stuff to the last slide. Okay, I moved and forget. Let me state the theorem, which is due to Matsumoto, I think. which is a key to study of the braid group. So assume that we have element W, which belongs to a affine while group, and this W has following decompositions, and this is it's a reduced decomposition. Then element TW, which is a product of TE1 and so on, TE chi, does not belong to, does not depend of choice of decomposition. This doesn't mean that we have an embedded. So it means that for any element of the affine while group, we can assign element of the braid group. This is not group embedding. So usually if we take two elements, W and W prime, and consider their products, then their lengths will be less than the sum of the length. Okay, let me state it as a corollary. If length of W prime is equal to sum of the length of W plus length of W prime, then TW prime is equal to TW prime. Is it clear? Now I'm going to apply it, but before maybe I should remark that the length one can define one can define length function of the affine while group. Extend affine while group. And in this, one can either say that this length function on the omega is equal to 1, or equivalently use property B. B is a minimal number of hyperplanes to cross from A to A prime. So if you take the group omega, which I have here, is a group which preserves fundamental Alkov. So for elements of this group, the length is equal to 1, to 0. Oh, sorry, I wrote here 1, then I should, let me correct this to 0. And exist braid group affine extended, which is generated by omega and all other t's. And for this group, the same is true. I don't know. Okay, let me stop. Are there any questions? Omega, yes, the group omega is a group which preserves fundamental alcove. So it permutes the hyperplanes on the boundary and the fundamental alcoves, hence it permutes simple roots. So the commutation relation between omega and T zeros is a permutation of the indices. So I can write it as a formula. So for any omega in the group omega, omega Ti, omega inverse is T omega of I. Omega permutes facets of A, hence omega permutes 0 R. And hence we can write this formula. This formula has thank you for question. There's any other questions? Yeah, so defining relations of this group are relations in this group omega. It is usually some finite group like C3. Braid relation between T's and commutation relation between omega and T's, which is like this. In principle, it could be symmetries of this triangle are 6, but inside with this way we obtained only 3. Only subgroup for the 3. We do not have element which is permutes alpha 1, which was the symmetry of the non-extended Dynkin diagram, which permutes alpha 1 and alpha 2. So in this case, we don't have, in the affine extended file group, we don't have such reflection. Yes, we can extend more. Yes. In principle, we can do it. Yes, sometimes this group also appears. So there's a bit more extended while group, and sometimes it appears. But we will not have more translations. This will, how to say, this will, so in terms of this decomposition, this will enlarge the factor W. You want to add one more, this reflection, one more hyperplane. Enlarge factor W. But for what I'm going to do, the most important thing is a translation, and this will not enlarge translation. Other questions? Maybe I can ask somebody in Zoom. I don't know. Kita, are you here?
Yes, I'm here.
Okay. Okay. So now I'm going to define this by lambda. definition for lambda, which is in P plus. So P plus means dominant. Let me define y lambda. Okay. Equals to corresponding translation. And for lambda in P, let us write it as the difference lambda 1 minus lambda 2, where lambda 1, lambda 2 belong to P plus. And then we can write that y lambda then define y lambda is equal to y lambda minus y lambda 2. Okay. And the proposition which makes this definition well defined is the following. So if we have two lambda 1, lambda 2 in P plus, then T lambda 1 in T lambda 2 commutes. So if we, what is the result of the corollary? I will explain this proposition, but I want to move to corollary. So, that map which we defined lambda to y lambda is a homomorphism from P to affine extended. So the naive map, which maps W to corresponding TW, is not homomorphic. It is impossible to find the while group inside the braid group, but it appears that we can find translation part inside the braid group. And this is, I mean, this construction is very useful. And this construction is based on what? So it's based on this proposition. So if we have two positive elements, then the corresponding translations, corresponding elements, commutes even in braid group. And if so, then, for example, here, this y lambda 1, y lambda 2 compute, so we can write product in this direction or on other order, it doesn't matter. Or, for example, if you take not lambda, if you have another decomposition, so say if lambda 1 minus lambda 2 is equal to some lambda 1 prime minus lambda 2 prime, then we have y lambda 1, y lambda 2 prime is equal to y lambda 2, y lambda 1, sorry, my lambda sign on the not subscript, superscripts, lambda 1, lambda 2 prime is equal to y lambda 1 prime, lambda 2. So the definition as a 1 lambda 1, y lambda 2 inverse is consistent with changing of this decomposition. Okay, is it clear? So what I'm saying is that if we prove this proposition, then this definition is correct, and we indeed map obtain the map from the lattice to the braid group. Questions? Yes, so our condition weights are dominant is leads us to the following. Let me rewrite this proposition. So it means that if we take the product, it will equal to T lambda 1 plus lambda prime, lambda 2. So hence, as I wrote before, T lambda 1, T lambda 2 compute. Yeah, so this embedding is not canonical. This map lambda to lambda depends on our choice of the simple roots. Yes, I think yes, there are other embeddings. So I think yes, I think they're just different. So I think there are other embeddings, and they're just different. Other questions? Yes. If, let me explain this proposition. I will try. Maybe I'll write proof in the final notes, which I put on the side. But the meaning of the proposition is the following. So, if lambda 1 is dominant, then the translation move us. This is a while chamber where dominant weight belongs. So this translation move us inside this chamber, and then there's some other one more chamber to move. And the number of hyperplanes which intersects will be the sum of number of hyperplanes which intersect in the first operation, and then in the second. So the length of the translation lambda 1 plus lambda 2 is equal to the sum of the length translation of lambda 1 and translation with respect to lambda 2. Hence this proposition is a corollary of this corollary. I correct my somehow mixed notations. Okay, I want to give a few problems about affine while group. So I prepared one problem and actually wanted to give another one. But I will spend remaining, say, 20 minutes to talk about lecture 3, which I also wanted. It's okay. I will correct. What? Okay, if you find any mistake in notes, and please write me. I will be very happy, and I'm absolutely sure there are many. Okay, I want to say a few words about representations, and I think I have not much time, so I will be rather brief. So there are two main kinds of representation of the affine Lie algebras. First one is a so-called evaluation, representation. If we have some loop group, loop algebra, we have evaluation homomorphism, which map any element of the form G of n to G times a power n, where a is some complex non-zero number, and k goes to 0. So if you look to the commutation relation of the algebra, I have them on the first slide of my last lecture. You see that k goes to 0, so we don't have this term. And in this commutator, we have a in power n times a in power b goes to a in power n plus n. So everything is this is a homomorphism. Using this homomorphism, starting from any representation of G, we can obtain representation of G hat. And this is called evaluation representation. There is a bit close, but a bit different way to talk about evaluation representation, which is the following. So if we have, so we can consider A not as a complex number, but as a formal parameter. So our vector space will be the space of polynomials, Laurent polynomials A and A inverse. And then this generator Gn acts as follows. And k again is 0. One can say that we have a map from this formal representation to just evaluation representation, which map formal parameter a to the complex number a, which is here. We have advantage and disadvantage. So advantage here is that this representations, if V is finite dimension, then this V is finite dimension. This is not. Disadvantage is the following. So if this representation of G hat, if you want to impose also action of the D to make it full Kac-Moody algebra, then this is impossible to define action of the D on the evaluation representation where A is a complex number, but for the case of the formal polynomials, we have this extends. I mean, now everything depends. So there's this notions are closed, but in some cases we have to use formal. In some cases, formal one. In some cases, we have to use this, consider A as a complex. For example, if you want to study finite dimensional representations, then you should forget about formal evaluation representation and speak about ordinary evaluation representations. Tilde differs from the head by the existence of the D differentiation. Difference between. Probably this is not almost standard notation, but it's not too bad, I hope. Here A means that A is a complex number. Yes. This is evaluation parameters. You know, like people write C2 of U when people talk about XX zeros. If you want to study finite dimensional representations, then you should think about evaluation representations, and the theorem which I state is the following. So irreducible representations are tensor products of the evaluation representations, and any irreducible representation is of this form. I wanted to say something about proof, but I think I have no time, so I skip it. I mean, I partially skip the proof, partially I give it to the problems, but let me give, instead of proof, give a remark. And remarks, this is going further, this will be true. I mean, true, it means in some sense, there's a natural analog for UQ SL2 hat, but not true in general. And this is probably quite unexpected. So for finite dimensional quantum groups, their representation theory are quite much parallel to representation theory of the simple algebras. And in the phi case, this normal for SL2 hat, it's okay. For G hat, the finite dimensional representations of affine quantum group, it's an interesting story. The check characters, it's an interesting story. It's not so simple as for the algebra. Okay. Are there any questions? Yes, I mean, this is just a remark for the future. We didn't define algebras. Yes. So I will repeat this remark sometime. Another class of representations are highest weight representations. So so here we have first, usually people define Fermat modulus. I will define them over the algebra G hat. This is M lambda K, where lambda belongs to the space dual to finite dimensional, Cartan, and K is complex number. And this M lambda K is generated by some vector V lambda K. Such that HI on V lambda K is equal to lambda of HI V lambda K, K on V lambda K is equal to K V lambda K, and all is 0 ER, any of them applied to V lambda K is 0. Yes. Here's a K capital, here's a K small. K capital is the element of the affine algebra, and K small is some number. This is standard definition. If you have a triangle decomposition of the algebra, n plus, Cartan and minus, then we can define the model saying that it is induced from the representation of the Borel subalgebra, or without such fancy words, but just. Okay, now let a lambda k be irreducible quotient of m lambda k. As usual, this is such quotient exists and unique. Remark that this is a different set of representations compared to evaluation representations. So let's take G equal to SL2 and V equal to C2. Then on the evaluation representation, element En goes to the matrix 0, 0, 0, A in power n, Fn goes to 0, 0, 0, A in power n, and Hn goes to A in power n minus n power n, 0, 0. Of course, I should make this remark, Rose's form when I talk about evaluation representations, but nevertheless, at least here. Everything's okay? No questions? So, okay, I have a question. Is this representation is highest weight representation? The answer is no. No, because so if we want, so I recall that the Borel subalgebra B plus is generated by E0, E1, H1, H2, so on, F1, F2, and so on. So it has both E's and F's. So if we take as usual highest weight vector, which is first basic element, it will be killed by all E's, but do not killed by any F's. And F's are here. Adjoint representation is somehow similar to evaluation because it also has level 0 and also don't have highest weight vector. It depends on what kind of algebra you consider. In principle, it is adjoint representation is close to formal evaluation parameter to find dimensional adjoint representation. If you consider coextended the algebra, so you take D but do not take K, then if K is equal to 0, then it will be a formal evaluation representation. So in the joint action, we have, if you forget, so this is representation is the extension of the formal evaluation representation. What I wanted to say is that in the evaluation representation, we have highest weight vector, which vanished by all these vectors. And in this representation, we have the highest weight vectors. In the highest weight representation, we have a vector which is vanished by all these vectors. So this is not highest weight. Okay. I want to say two last things. First thing that there is an explicit construction of level 1 representation. I skip here any details, but I leave as a problem to check it for SL2 case. And the second thing which I wanted to mention, and there are vertex operators, which maps. I mean, there can be defined in different direction, but which map from the tensor pro this direction from the representation highest weight to the tensor product of the representation with the evaluation representations. And this matrix element of this vector operator satisfy KZ нижних замолочков equations. And later we'll talk about quantum groups. I hope we will come to the Q deformation of KZ equations and Q deformation of the vertex operators. But I'm not, I mean, I think I'm over time. I think people are tired. So I stop here and I will see you next time whether I will talk more about vertex operators in class or I will put them in problems and then wait for Q story. Questions? Okay, if there are no questions, let me stop screen sharing.